Hello. Hello, everyone. It's wonderful to see you all here. I hope you're excited for this workshop as much as I am. I will be posting the event code right now and halfway during the workshop. I'll also post the mobile app links in case it's needed. Feel free to ask questions in the chat. And now I'll give it up for Rittika Adhikari to take the stage.
Hi guys, I'm Rittika, and today I'm going to be talking about how to make a handwriting to text recognition system. So a little bit about me first. I'm pursuing a BSMS in CS. I just started the MS part of that this semester, and my primary research interest is in ML. I mostly work a lot with interpretability and fairness in ML, which means I work on trying to make sure that models are interpretable and understandable and trying to be able to explain how machine learning model decisions have been made. And for fairness, I try to ensure that all of the model's decisions are fair and unbiased, even if our data is biased. I've also done a little bit of work in federated learning with an application to medicine. Most recently, I'm part of Professor Sanmi Koyejo's lab, where we're working on creating a secure federated learning system to diagnose COVID-19 from chest x-rays. So that's a little bit about me. So let's get right into it. So here's a really quick intro to neural networks for those of you who are not familiar. So over here, we start with like the fundamental building block, which is a neuron, where given some input, it just applies a function and returns some output. So in this situation, we just first start by multiplying each input by their respective weight. Then we combine the weighted inputs with some bias, and then we pass in the sum that we got from step 2 into an activation function. And we get like something that looks like the line like right below, which is just f of w1 times x1 plus w2 times x2 plus b, where f is the activation function. And we also have some examples of activation functions, such as the step function, sigmoid, ReLU, etc. This is known, this whole process of like moving inputs into the neuron and like getting an output, this is known as like a feed forward process. So you might have heard the term feed forward neural network. This is where this is coming from. So a neural network, basically just given some input, will apply a chain of neurons and then return some output. And we have something called a hidden layer, and you can have multiple of these. Hidden layer is basically just any layer in between the input layer and the output layer. Right now, let's think about what would happen if we pass in x equals 2, 3. So first, what would happen is to compute h1, we would place an activation function on w1 times x1 plus b, and then do the same for h2, but for x2 and w2. And then our like final output would just be h1 and h2. Now that we know how to get our outputs from our neural network, we also need to consider how we can quantify how good our neural network is doing. So we can do this by using something called a loss function. So one example of this is mean squared error. So did it just stop sharing?
Oh, sorry, try again.
Okay, yeah. Okay, cool. Can you guys see my screen now? Oh, okay. Cool, awesome. Yeah, so we can, so we want to quantify how good our neural network is doing. So we can use something called a loss function. So one example of this is mean squared error, which is just the mean of the square difference between the true prediction label and the predicted label. Yeah, and essentially, the smaller your loss, the better your predictions will be. So we want to minimize the loss. So how do we do this? Yeah, so like I said, we want to train a model where the loss is minimized. So how can we update our model's parameters, so W1 and B and all the biases, et cetera, in order to decrease our loss? The answer is backpropagation. Basically, we want to compute the gradient of the loss with respect to the parameters and minimize the loss using the gradients. So some examples of optimizers are SGD, Atom, cross entropy, etc. So that's the basic structure of a neural network. Does anyone have any questions? Okay, cool. Then we will move on to the, what was the gradient? So we find the gradient of the loss with respect to each parameters. So it would be like just the derivative of the loss with respect to like W1, for example, and then so on and so forth. That's how, and then you want to minimize that in order to, yeah, minimize the loss. Yeah. Yeah, okay, cool. Yeah, that being said, let's move on to the demo, but feel free to comment in the chat if you guys have any questions on the previous stuff. Yeah, so I'm not actually gonna run the demo right now because it takes a while to train, but this is basically a really simple neural network that I made on CFR10. And CFR10, if you guys aren't familiar, is just this data set with 10 different image classes, which is airplane, automobile, bird, cat, dog, deer, frog, horse, ship, and truck. And I've adapted this from the PyTorch beginner tutorial. Yeah, so over here we have our imports, which aren't super relevant. But the first thing you need to do is you need to load in your data. And PyTorch, which is the framework we're going to be using for our activity and our demo today, has this thing called a data loader. So first you can load in the data set. PyTorch has like a function called CFR10, which will allow us to like automatically download the data. But you can also create like image folders if you want your own custom data set, which is what we'll be using for the latter half. But yeah, and then you can create a custom, you can create a data loader from this data set. And over here, you can also specify the batch size. The batch size is basically the number of images you want to process at a certain amount of time. So by default, I set it to B4. And when you run this, it'll download your training data into like some folder, and it'll also display a few images when plot is true. And then over here, we have a simple CNN structure, which basically has some conv network, conv layers, pooling layer, and some linear layers. We'll be going a little bit more into the actual mechanics of a CNN a little later, so I will kind of gloss over that. But as you can see over here, we're just applying all of these layers onto like the original data, kind of like in the same structure I was talking about with like the neurons. So basically you're just applying the weights, the bias, and then you're applying some kind of activation on that. And that's the general framework. Yeah. To train using Colab, there are also some GPU resources available. So you can specify the device using something like this, and you can create the model and you push the model to the GPU. And in this case, I used a cross entropy loss, and my optimizer was using SGD. I set the model to training mode, and you basically just loop through while keeping track of like the total loss per epoch. And you loop through each of the batches. You loop through each of the batches, and then you first zero out you first have to zero out the gradients. Then you do a forward pass to like get like the outputs, and then you do a backward pass to compute the difference between the outputs and the labels, and then you do lost step backwards. And let me post it again. But yeah, this is yeah. But yeah, so you do the backward pass, which will update the gradients, and then you do the optimizer depth step, which will update each of the parameters of your network. And then finally, I just print the statistics every like 4,000 mini batches, I think. Yeah. And then I also save the model. Typically, you should save your model, and you should probably also checkpoint if you're trying to create like a really a model that requires like a lot of training, and takes a lot of time. You should probably checkpoint so that you can, so that even if like your process like fails or like dies for a random reason, like you can restart from the checkpoint and not like restart from the beginning. So just some things to keep in mind. But that's the general training paradigm. Just make sure you zero out the parameter gradients. I've had one too many bugs from forgetting to do this. This is really important because otherwise your gradients will explode. But yeah, that's the general training framework. For testing, it's pretty similar, except you specify that you set to evaluation mode, and then you specify that the backward pass won't modify the gradient with this thing called torch.nograd. So it won't like update any gradients here. And basically, you move your data to the appropriate device, you do a forward pass, and then this time you get like the actual predicted label, and just compute like this is how we can compute the correctness across classes, across like our entire mini batch. And then just I'm also computing the correctness per class because I want to see like a class by class breakdown. And then I just print out both of these things at the end. Then finally, we have prediction, where basically I just use Pillow, which is another Python package, to load in my image. And then Colab has this like magic display function, but normally you would do im.show in Pillow, but im.show doesn't work in Colab. So they have this magic display function, which you can use. And then I apply this transform and to the image, because I had to apply it when I was loading my data as well, to like have the data all be like, so the data provided was already the same size, but you also want to make sure it's like normalized, etc. So you have to apply that transform. But I also added a transform here because my image might not be 32 by 32. So I added that, and then I move everything to device, and then I try to do a forward pass in order to get my final prediction, and then I can just print that out. And classes is a global variable I defined a while back. And I also have like some code to load a model from the existing thing. So here's just an example run of the pre-process, train, test, and predict whole paradigm. So over here, I like loaded the data, and so what the Python PyTorch data set does is it will download the data, and then I also like displayed some example images. They're kind of blurry, but you can kind of make it out. So this is from the train set, and this is from the test set. Then I just called train, like my train helper function on the train data loader that I got from here. And and then every like a few batch indices, it would print out like the loss and like the epoch that it's on. Oops, I am sorry, let me close that. And then I evaluate the model using my test helper function. So the overall accuracy was 62.39%. But here's like a class by class breakdown, so we can see like where it's doing well, where it's suffering. Like as you can see, it's kind of suffering on like dogs, cats, birds, but like other images, it's doing okay. Yeah, and then I decided to try and classify my dog. So this is my dog. His name is Frankie. Um, I yeah, and I call my predict function on that, and he is a dog. So yay. Um, yeah, so it works well enough to predict him. Um, yeah, that's all I had for the demo. Does anyone have any questions? Yeah, go for it. The type of learning I was doing for my research, do you mean were you talking about interpretability or federated learning? Federated. Okay, so federated is basically a modification of distributed learning. So like the general idea is that you have like some kind of server and then you have a bunch of clients. So in the hospital setting that I'm working in, like the server would be, I don't know, somewhere, but the clients would each be like individual hospitals and they don't share any data. So that's like the tricky and interesting part about that. Because your data will have like very different distributions. And so normally what you would do, maybe like you train a model per hospital, but perhaps like other hospitals have some information or some data that you like would not originally get from the current hospital that you're at. But there's like this tricky part where you can't share data because of like HIPAA compliance, like, right, it's not secure. But federated learning would allow us to basically train our models in some kind of process and then share the model like weights in a secure manner, so that we can aggregate all of that and like create like a better model that's like robust to like all the images without the server ever actually seeing any of the data and without the hospitals, yeah, without the hospitals actually like sharing any data. But that's federated learning in a nutshell. But it's cool stuff. There's this really cool Google blog that I like little Google comic. I can look it up after and send it if you're interested. Yeah, no, it's fun. Yeah, okay. Any other questions before we move on with the workshop? Okay, I will move on then. Feel free to type in the chat if you guys have a question. Cool. Okay, so our agenda for today, we'll just talk about what we're trying to solve, what are convolutional neural networks, how do we design a convolutional neural network, how do we train it, and how do we utilize our trained CNN to predict, and just some conclusions. Yeah, so we're trying to build a handwriting to text recognition system. So basically, given some sample image of handwriting, how can we convert it to a sequence of letters automatically? So say like we're given this like image on this index card with like hello world written out. How do we convert it into hello world in text? Um, yeah. So what do we know already? So this is a supervised learning problem because we already have this data set called emnist. You guys might have heard of emnist, which has like the numbers. emnist is basically extended emnist, which has like letters and stuff like that. The label data set of each character in black or white. And we also have our sample image, which we want to predict. So we have a decent amount of information. So our first step would be to train a model on emnist. So we want to train some convolutional neural network to predict the letter that 28 by 28 grayscale image represents. 28 by 28 just because that's what EMNIST does, so that's what we resize to. Um, but yeah, as you can see, basically we have this like input and we pass it in through each of the layers, and then we want to get some output like label from 0 through 25. Sorry, that's a typo. That should be 0 to 25, where the image will correspond to the specific letter. Um, yeah. And then our next step would be to process our provided image. So as you can see, like kind of like just from the EMNIST data, like you can see like they're all in black and white, colors are inverted, there's no lines or any noise really in the background. So we kind of want to get to that point. So the way we do this, just really simplified, we first convert the image to grayscale and then we remove all of the lines from the background. As you can see, it's not perfect. Actually, we use this version of OpenCV that has like this line segment detector, but it was removed in a later version of OpenCV. Um, but because of some weird, like I think I don't know, there's something weird going on with like I don't know, information. I don't know. But yeah, so we use that line segment detector to detect and remove those lines. So we detect them, then we create a mask, and then we remove them. And then we separate everything into bounding boxes by first using CV to detect bounding boxes. And then we just use like something like non-maximum suppression to get rid of any extraneous boxes. Because I don't know if you guys have ever tried to use CV2s to detect bounding boxes, but what it normally does is it has like a bunch of like tiny little boxes. It will capture like, and they were like often overlapping. So we want to find the non-overlapping things. So that's why we use non-max suppression to get those boxes. And then finally, we crop to the bounding box size. Then we resize them, and then we invert the color of each character to get it to look a little bit more like our EMS stuff. Yeah. And then our final step is to use our model for inference. So we pipe in each cropped image into our train model to predict the corresponding letter, and then we print our final prediction. So ideally, we want something that will like pipe in each of those like cropped images to correspond to some letter. So that's what that looks like. Yeah. So a little bit on convolutional neural networks. Um, as you guys know, an image is a 3D matrix of values between 0 to 255. In grayscale, this is 1 by height by width. And there are 26 classes, one per letter. And our input will typically be n times 1 times h times w, because there are like we process n images simultaneously. This is like our batch size, like I was mentioning earlier. And our output is n by 26 probabilities, one corresponding to each like image. Yeah, and we want to train our network to maximize the probabilities of the correct letter, and also thereby minimize the loss. So a little bit on our convolutional layer. So we have something called a convolutional filter, and this will iterate over our input matrix and just produce an output that's slightly smaller. K filters will yield a k-dimensional output, and the output features of one layer should match the input features of the following layer. Yeah, but essentially what you should keep in mind is that like the output dimensions of the previous layer are the input dimensions of like the next layer. So that's one main thing to keep in mind when building convolutional layers. And now we can move on to the actual activity. Well, the first part of the activity at least. So let me share the collab link. So you guys can just do file, save a copy in Drive, and we can work off of that copy. And then once you guys get there, make sure you do runtime change runtime type to GPU because you will need GPU. If it's on CPU, it will like take forever to run. But like first run these cells and then it will update with like the OpenCV version that we need because of line segment detector. Um, yeah. So I'll give you guys a few minutes um, to go and do that. And then you guys can also just go ahead and run the data preparation and data and neural network loading things. If we have time, I can talk a little bit about what I did for that logic, though I like breeze through it a little bit. But first, I guess let's try to finish the activity first and then I can go back to that. I guess just press the thumbs up button if you guys have like made a copy and run like the first 1, 2, 3, 4 cells. So you can use the Zoom participants thing and just give me a thumbs up if you guys are ready to move on. Oh, it says you need to request access. That's weird. Okay, I thought I was looking at the wrong. It should be available to anybody, I think. Maybe let me just change it to be anybody can access this. Um, does that work? Yeah. Okay, cool. Yeah, and just do the file, make a copy, make sure to change your runtime type because that is very important. Yeah, just give me a thumbs up if you guys are good on running those few cells. Okay, it looks like few of you have gotten it. I think I will move on, but comment in the chat if you guys are having any issues um, with running those first few blocks. Shouldn't run into any compile issues that would but yeah. Okay, so for the activity, we have this thing called an emnist block, which basically has a cont filter. So you specify in features and out features. We have a default kernel size and stride. And basically, we created this emnist, which has a bunch of emnist blocks. And we want you to I think everything that's like a blank over here. So we specify the out features here. So you guess what the in features are here. the out features for these blocks. Yeah. So I'll give you guys maybe until like 4:32 to kind of think about and try filling in these blanks, and then we can sync back. Yeah. Okay. Yeah. Does anyone know what the in features should be here? Um, okay, so this one should be one because this is like our first block. Um, but remember what I said about the out features being the same as the in features for the next layer. So can anyone guess what the in features should be for this layer? Or like, well, this block? Yeah, should be 32. What about the out features for this? 64, perfect. What about here? 128. And what about this one? Okay, yeah, that is pretty much it for that part. So you can run that block. Yeah, and we can move on to the next part of the presentation. Okay. Um, so we already talked a little bit about the training loop, but basically our primary goal when training is to think about how we can minimize the error of our network. Um, so since neural networks are differentiable, we want to just move the weights in the direction of the negative gradient. And there are four components that we need to consider when we're doing this. That's the model prediction, so our outputs, our ground truth, our loss function, and our optimizer. So a traditional training loop basically just clears the gradients in the optimizer using optimizer.zeroGrad. And then we can compute the loss between the model prediction and the ground truth. And then we run the loss top backwards to get the gradients with respect to all of the weights in order to actually minimize the loss. And then optimizer.step will allow us to update our gradient, update our parameters with respect to the gradient. So that is the general training loop. Does anyone have any questions on that? No? Okay. Yeah, so the next part of this activity would be to just train our model. So this is your to do. So I guess just to go over what I'm doing here as well. Basically, we set all of our labels to be 0 indexed because initially there were numbers from 1 through 26, but we want them to be numbers from 0 to 25. And then we just create a model. Then we create all of our train batches by just creating using our provided like xtrain, xtest, ytrain, ytest. So in this case, I think there were already NumPy arrays, which is why I used torch.from from NumPy instead of actually using the data set thing I was telling you about from the demo. But yeah. So I use that, and then I moved my model to device. And then I decided to use the Atom Optimizer, and basically over here, we just like go through each epoch. There's this thing called TQDM, which shows a progress bar, which I'm using to output stuff, output like the like losses and how many of the epochs have been completed. Yeah, so we go through each batch, and this is where you guys are going to have to run through the network and initiate the backward pass in order to update our gradients. And then over here in this segment, we basically just test and evaluate our model by just going through all the test batches, running our inputs, looking at the batch loss between that, and we also see how many things are correct, how many of our predictions are actually correct, and we also log that using similarly also using TQDM. But yeah, I think I'll give you guys maybe until like 4:40 to work on this part. Yeah, I'll leave this on this slide because this will probably be helpful. Yeah. Okay. Can anyone tell me what the first step will be here to get the outputs. Okay, to do a forward pass, you basically just pass your inputs um, through the model like this. So model of ends equals output. So that's how you get the outputs. Then, oh yeah, but more importantly, before you have to do optimizer.zeroFrag in order to zero out your gradients. Then you want to do a forward pass. And then after your forward pass, you want to compute the loss. Does anyone know how we can compute the loss? Okay. So we've defined a loss function, but it basically just takes in outputs and labels. I think that's the right order. Yeah, it's the predicted and then that, and that's how you get the loss. So this is how you can update the loss. Does anyone know how we can get the backward pass? So to do the backward pass, we can just do loss step backwards, and this will update the gradients. And then finally, we just need to step to update our waves. Yeah, that's it for that section. And then I think for predict, there's one last part. Okay, so given some optimized model, how can we predict a letter? So recall that our network produces 26 probabilities for each letter. So which one will we pick? Well, we want to pick the one that has the maximum probability of occurring, right? So we use this function called torch.argmax in order to get the maximum probabilities. So yeah, so I think you just need to do that over here to find the index of the letter with the highest classification probability. So you could just do torch.argmax of probabilities to get that. Does anyone have any questions on the prediction loop? No? Okay. Yeah, I think there is one, I think I have to show you guys there's like a hello world image example that you guys can use. Let me just share that image with you guys so that you can upload it. So this is a link to the Hello World image. If you guys could just download that, then once you download that, actually maybe I should download that. Um, okay, so once you download that, you can click on the files, click on the upload button, click on downloads, you can add Hello World. So once you add that there, you can just run train. Training will take at least like 5-6 minutes. So should try to run that. And then you can just run this, and it will take hello world.jpg as the input image. Yeah, and that's pretty much it for the actual demo. Have you guys all gotten to the point where it's training successfully? Give me a thumbs up if you have. Okay, cool. Seems like a lot of you have gotten it to um, train. Okay, cool. Yeah, that will probably take like 5-6 minutes. In the meantime, I have one more slide. Okay. My last slide is basically, well, if you enjoy ML or are thinking about how you can get more involved and learn more about it, some clubs are like SIG AI or SIG NLP, which might be fun to join. And then if you're interested in research and getting involved in that, I would suggest Pure if you're a freshman or sophomore. Spin, I think, is with NCSA or just talking with professors who work in areas you're interested in. I know plenty of people who have just sent professors like emails where they like talk about like, hey, like I read like so and so papers and I was really interested in this content and I'd really like to work with you. So I think, uh, yeah, so something like that. Um, yeah, that stuff like that also works. Um, I personally got started and involved in research through Pure. Um, they basically assign you with a PhD mentor, and then your PhD mentor will like help you through a project for a semester. It's like a 1 credit hour course, and you just make a poster at the end, and then I ended up meeting Professor Sunmi because he was judging my poster and was interested in the work. And that's how we ended up working together. But yeah, reach out to professors if you're interested in their work and want to work with them. Uh, Professors here are really, really nice. And they will typically be willing to talk, especially if you're taking a class with them. So definitely reach out to them. Other than that, for classes, I would recommend if you're interested in a combo of theory and applied classes, I suggest like classes like 440, which is AI, 445, which is computational photography, um, AML, deep learning, trustworthy ML, or like 543, which is a little bit more the theory side, but you also get to do a lot of cool like projects too. So it's fun. If you're looking for more theory and like proof style stuff, then I'd recommend like 446, 447, RL, or 540. 540, I think, is like in your class. Yeah. Okay. I noticed that there's some questions in the chat now. Sorry, I missed this. He is asking, is there any methodology that helps you decide how many filters to use in the convolution layers? I assume it's increasing complexity. So yeah, there is. Sorry. I'd say it's kind of like um, just guesswork kind of a little bit. It's kind of like tuning to see like, where the breaking point is. Like, yeah, like more filters can also like mess things up too. Like if you have too many like convolutional filters, like you might end up like disregarding like some important features, etc. So like there's like a point at which I guess more is more is too much. But yeah. Yeah, it's like fine-tuning a parameter. I also typically also I wouldn't recommend that you write conv nets from scratch. I know that that's what we did here, but typically and I mean I guess we're doing that more so for like simple tasks like handwriting, but like for more complicated image tasks like with what I did with my dog, like trying to classify my dog, I think it I would have had better accuracy if I had um used transfer learning on a pre-existing network like ResNet or DenseNet or something like that. And there are lots of resources for doing that. I really like the PyTorch tutorials. I think they're pretty useful. They also have like ways that you can run those on Colab too. So you don't even have to like write out the code even if you don't want to. Um, yeah, so that's pretty much all I have for this. Yeah. Let me know if you guys have any other questions. Oh yeah. Also, mine just finished running. I don't know if yours finished running yet, but I got my Hello World. As you can see, it is not able to predict spaces. But but yeah, it did get the text at the very least. But it is a little temperamental, so I'm not entirely certain that it will work perfectly if you try running it on other things. Um, yeah, yeah, yeah. Coding up models from scratch is typically worse. Like I would not recommend coding up models from scratch. Like I think for MNIST and like EMNIST, those are like simple image tasks. And sometimes like models like DenseNet can be like too complicated for that. Like that's like overcomplicating it. So that's why sometimes for models like that, you can write your own networks. But I would say for like problems like complicated images, it doesn't really make sense. Yeah.
All right, okay. Thank you so much, Rittika, for this amazing presentation. If you all have any questions, feel free to stay back. Otherwise, have a great day.